Hello everyone, my name is Sheldon, and welcome to CAC 2515, Introduction to Machine Learning. In this video, I'm going to walk through the implementation of k-nearest neighbors algorithm. So let's begin by setting the random seed. So in Numpy, in order to reproduce the results, we set the random seed to a specific number, and so as long as you have this number to be the same, all the randomness is fixed here. So let's first generate the data for the algorithm. So we write a function that takes in the number of data points you want. So basically, this will return the two clusters of Gaussians. So the first argument is the number of points in the first Gaussian, and the second argument is the number of points in the second Gaussian. And this is done by basically calling numpy.random.normal. So this function here will return a Gaussian distribution. I mean samples from this Gaussian distribution centered at 0 with standard unit variance 1 and of size 2 by n1, which is the number of points for the first cluster, and then we'll shift this Gaussian distribution to 1, 1 here, so that it will be a Gaussian distribution centered at 1, 1 instead. And we do the same for the second cluster, and we shift it to -1, -1. And then we generate the labels by calling numpy.zeros n1, which will return a vector of zeros of size n1. And the same with the y2, the labels for the second cluster, it will return ones of size, a vector of ones of size n2. And then we stack them together to form the dataset. So this is the first cluster of Gaussian, this is the first Gaussian cluster, and this is the second cluster. And it's always a great idea, it's always a good idea to visualize your data set before doing anything, so that you know what's going on, and to make sure the data is generated the way you thought it's generated. So here we call the function and generate the data. This is the training data, and then we do the same to generate the test data. And we then plot the data and basically visually inspect whether it's two Gaussians, and they look pretty much like two Gaussian distributions, so that's great. And we also had this helper function called plot data to plot the data given the data and the labels. Okay, and the first thing we need to do is, after the data set is generated, we need to implement the distance function. So because the distance measure, the distance function is the critical component in the k-nearest neighbor. It's really important for the algorithm. The performance of the algorithm is basically partially determined by whether you have a reasonable distance metric. So here are 3 ways to implement the distance function. They are equivalent to do the same thing, and they're just 3 different ways of implementing them using different libraries. So the first one is using Numpy, and the second one is using the linear algebra API, and the third one is using SciPy. And this is also pretty straightforward. You just take in you 2 matrices where each matrix XA and XB represent the data points. While here we're kind of assuming XB is 2 by 1, and this is 2 by a number of training data points. And we take the difference of them, square them, and then sum along the first axis, because the first axis represent the row axis. Like you want to sum over every single row, because the number, like the columns, like not the columns, but different rows will represent different data points. So you don't want to sum over across that dimension. You want to sum over the you want to basically sum over the rows. And I think one way for me to basically think about it is that whenever you sum over a particular axis or take the max or whatever, you do some operations on a particular axis, this is basically collapsing that axis to a single point. So I think maybe in that way it will be easier for you to think about those vector array or tensor operations later on. So yeah, and yeah, so those are three different ways to do that. This square root here is not strictly necessary because all we care about is the ranking of the distances, not the distance themselves. So it's not necessary, but for completeness, we're still putting the square root here. And here we're just choosing one of the three distance functions. Okay, now we're going to write the function that predicts the label using the k nearest neighbor algorithm, and we are going to do it one at a time for now. So this function takes in the dataset and the label and takes in the query point. Note that here we are basically limited to 1 point, and k is the number of neighbors being considered. So first of all, we need to reshape the query point to make it 2 by 1 instead of 1 by 2, because then it will be able to broadcast with the data. And then we call the distance function with the data and the query point, and that will return you a vector of distances for this point. And we then call numpy.arcsort, which sort all the distances, the distance vector, and return the index. So that's arcsort, and we are basically calling. So after this vector of distance is sorted and the indexes are returned, the arguments, meaning the indexes are returned, we take the top k. So that's basically the indices of the top k points among all the data that's closest to the given query point. And then we use this index to select the training labels, to select the labels. So the y votes will be the labels of all the k nearest neighbors points to the query point. And then we do a counting by using numpy.unique, which basically basically counts the number of occurrences of each point. And you need to specify that by basically putting the return counts as true. And this will return how many times each point is occurring. And in our case, the votes are either, our votes are the labels, so it's either 0 or 1. So basically, it will return 0 or 1, and then we take the max of the counts. Basically, do you have more number of zeros or ones? And that will return you an index, and you put that index into the votes, and that will give you the label corresponding to the prediction. Basically, the label corresponding to the label that has the maximum vote, and that's basically your prediction. So that's the function that does k nearest neighbor prediction. So now we call this function to make the prediction, and so we select a point from the test set. So remember, the first axis means the rows. So this is the NumPy selection syntax. So this basically means select everything in the first dimension, because the first dimension, the zeroth dimension, because the Python goes from 0, means that select both data dimension, and the second dimension is the data set dimension, different between different data points. So we're basically selecting one data here. Well, you can do it this way, but then it will return a vector of size 2, and that won't be able to broadcast it with the data matrix over here. So we can do it this way so that it will return a 2 by 1. It's still a vector, but it's have extra dimension so that it can be broadcast. This can broadcast. Well, you can also add a new axis, or there are different ways to do this, but this is just one way to do this. After that, we just call the function. We pass in the training data set, the labels. We pass in the query point, and we specify how many neighbors do we want. And then they will return. This will return the prediction, and then we plot the data. We plot the training data, and then we plot the prediction over here using the prediction. It's shown on the plot over here. It's a green cross. So as you can see, it's being labeled as class 0, and indeed it looks like it's from, it looks like it's from this blue cluster, class 0. So, so that's that. Now we want to write a function that does multiple predictions at a time, at once. So before that, we need to modify the distance function, because previously the distance function only works for one data point. So the naive way to do that would be just modify what we've done over here, because now situation is a little bit different, because previously this m used to be 1. So we basically want to take the difference between every point in M with all the n different points in XA, the training data. So the naive way to go about that will be adding new axes. So we can add one axis after n here, and add another axis here before m, so that basically they will nicely just do what I just said. Like each point in here will be compared with every other point in the training data. But the downfall for that is it will take up a lot of memory. So a better way to do that would be do a little more of derivation and expand out the quadratic to make it xa squared plus xb squared minus 2xa transpose times xb, which is the cross term in the quadratic. So, and then we don't have to to do this to use more memory. We can just square this and take the sum and reshape, and then square this, take the sum, and then compute the cross term by doing the dot product of the xa transpose xb, and then we just return them all together, and that will just give us the a distance matrix where the first dimension is the number of data points. Oh no, sorry, the data point of the number of data points in the training set, and the second dimension is the number of data points in the test set. So basically, for every point in the test set, we want to find top k distance in the in this matrix. Okay, now let's run the function itself that will make multiple predictions at once. So we take the distance by calling the distance function with the training set, and in this case, it's probably going to be we can do a huge test set of multiple points. So it will return a matrix n by n matrix, where whereas like I talked about before, it's the first dimension is going to be the number of points in the training set. The second is the number of points in the test set. So now we want to figure out the indices. So we use the same function, but now we have to specify another actual argument axis, meaning that we're doing this along the first axis, the zeroth axis. Well, okay. All right, I'll just say the zeroth axis, even though it's not correct in English, but it's correct in Python. Okay, so what that means is you are collapsing, just like I said before, you can think of it as you are collapsing a particular axis. So if you collapse the first axis, it's basically squashing them into one dimension. And in this case, in this case, you're sorting along this dimension of n points. I mean, you can think of it you can think of it as a matrix where each row is the distance to a particular point in the training set for every single test point, and each column is the distance for a single test point to all the other points in the training set. So when we are collapsing the zeros axis, we are taking we are basically doing the sort along that dimension, that direction, along columns. And then when we take the top k over here, where we are selecting the top k distances, and because they're sorted from small to big, so top k just means the smallest k distances, and because this function returns the index, so the index of the smallest k nearest neighbors. So this is what this k means, and the second argument is basically saying keep everything else along the second dimension, because you want to do that because the second dimension is the test set dimension. And then we do similar things. We take those indices and we plug them into the label matrix. So this is a bit of Numpy magic where this is like a selection indices vector, and then you plug that into the label matrix, and that will return you the labels in a form of matrix. Sorry, this is not a vector, this is also a matrix, in fact. So so now, this time we're not going to use the numpy.unique, we're going to do it in another way, in a more Numpy magic way. So basically here, this is a matrix, right? So you might ask, what does it mean to compare a matrix with a scalar? So in Python and in Numpy especially, this is like broadcasting. So when you're comparing a matrix with a scalar, this is just comparing this scalar to every element in this matrix, and then put a 1 if this is true, put a 0 if this is false, because 0 and 1 here stands for the Boolean true and false. So that will also return you a matrix, and you do a sum over the zeros axis, which basically gives you the count for a number of zeros, and you compare it with ones, and it gives you a count of number of ones. So whenever you're doing a sum or mean or whatever operation along a specific particular axis, remember I said it's kind of equivalent as crushing that particular dimension. So this is basically returning a vector. And it will be clear here that if you crush the n dimension, like dimension of n elements, which is the training set, so basically it will return you with a vector of size n. And this is here we're just doing this again, like evaluating this argument. Like previously we're evaluating equal, now we're evaluating smaller than. So this is basically comparing every element, like the first element here and the first element here, the second element here, second element here, and then put a Boolean 0, 1 into the vector as the prediction vector. So this makes sense because if you think about it, if there are more, this is basically English, like if there's more ones in the first element, like meaning the first test point, than zeros, then this is true, this will return 1, right? So it's like, it looks a little bit confusing in the first glance, but if you think about it, it's actually pretty straightforward. So that will return you a vector of prediction labels, 0 and 1s, and that's basically it. That's the function that will do multiple prediction using the k-means algorithm. Sorry, k-nearest neighbors algorithm. So after we have this function, now we can go. We can move on. We use this function by just calling it with the entire training set, training label, and the entire test set, and we can specify whatever k we want. And then we can plot them. We can plot the training data as usual and call it train, and we can plot the test data, but instead of using the test label, we use the original test label, we use the predictive label. And then here, as you can see in the plot, the blue cluster is the original cluster for class 0, and the orange cluster is the original cluster of labels 1, and the green points are points that were predicted as class 0, and red points are predicted as class 1. And then, as you can see, it kind of makes sense, right? All the green points are very close to the blue points, and the orange points are close to the red points. I mean the other way around. But there are certainly some outliers, as you can see over here. But in general, this looks pretty reasonable. So now we want to plot the decision boundary of our k nearest neighbor algorithm. And I'll try. So this function does that, but okay, I'll try to explain as much detail as possible. But if you are feeling confused, you can just you can look up any specific API just by Google it. It's really clear. Or you can also ask questions during the tutorial. So this is done by first determining the range of the windows. Basically, to plot a decision boundary, this is done by kind of coloring. You can think of it as like coloring every pixel. So that's the way I think about it. So each picture is made up of pixels, right? And so when you want to plot the decision boundary, you want to assign a label to every single pixel, right? Like every single pixel, meaning every single point, 0 or 1. And when they differ, when they differentiate, that's when you have a boundary. That's when you have a point on the boundary. So that's done by, again, first you have to determine, okay, so what's the range of all the pixels you want to do that. So here we just select the minimum and the maximum of the training set. 0 just means x-axis. So basically, like, I think here is the smallest point on x-axis for the training set, and we select that and we -1. So that's the lower bound of x-axis, and we do the same. We add 1 for the maximum, and that will be the upper bound for the for the x-axis, and we do the same for y-axis, and then that will give us the range of our picture, the range of the image, and then we call this numpy.meshGrid function to give us a mesh grid. So like the pixels, you can think of it as pixels, and then we stack them together to become a mesh grid, and then we treat the mesh grid, which is the pixels, basically a lot of pixels, and we treat that as a test set, basically, the test data point. We're asking the algorithm, the function we implemented before, to predict label for every single point in this mesh grid, and for k, the k specified here, k nearest neighbors. And after we get this prediction, we just need to plot them out, right? Like whenever there's a difference, that's the decision boundary. So, and that can be achieved with the counter function over here. I won't get into the specific details here because they're not as important, but if you're curious, you can look it up. But basically, that's just what this function is doing is look at where 0 turns to 1, so look at where there's a differential, basically, and that will give us the decision boundary. So if we apply this function on one nearest neighbor, this will give a decision boundary that kind of look like this, which is pretty noisy, and this is also mentioned in lecture. And when you have a outlier like this, because it's very noisy because it will disturb the decision boundary. It will kind of because apparently here, if you have a point here, it will be clustered as it will be predicted as a from the blue cluster, but where it should be from the orange cluster. As you increase k, the decision boundary got a lot smoother. So this outlier here will no longer have such a big impact on the decision boundary. And as you put it to change it to 5, that will even be better. The decision boundary is even more smoother. It's much more smoother here, and will allow more outliers, ignore more outliers. And that's it for the implementation for k-nearest neighbors. Thank you for watching.